Okay, let's look at this problem here. A Christmas light emits a photon at a frequency of 3.74 times 10 to the 14th hertz. And then I'm going to ask three questions. First one, what is the wavelength in nanometers of each photon? How much energy is in the photon? And number three, how much energy would that many moles of photons contain? So you almost for sure are going to get a question like this on your test. And I think these are not hard problems to do. You just got to be familiar with the terminology. And so let's do that real quick. Let's get familiar with the terminology. So again, it's important to remember that this Greek letter nu, that is the frequency. Okay, and then the other thing we're dealing with often with light is the wavelength. What is the wavelength of the light? And that is given by the Greek sign lambda. And so the equations also to be familiar with is the first one that we will have to use likely is this: speed of light is equal to the wavelength times the frequency. Speed of light is a constant, so you're always going to know that, and that's given by 3 times 10 to the 8th meters per second. That is the velocity of light. So the other equation we're going to have to get familiar with is the idea of energy. And energy equals Planck's constant, which is h, times the frequency. And if we rearrange actually this equation right here, then we also know that energy is equal to Planck's constant times the speed of light divided by lambda. And so it's really just some algebra. It's understanding what's going on and doing some algebra. And so let's tackle that first one. What is the wavelength in nanometers of each photon? I give you the frequency, so we can use that equation. We can say that C equals lambda, the wavelength, times the frequency. I want to know lambda, so I can rearrange that equation and say that lambda is equal to the speed of light divided by the frequency. I've given the frequency, so we know that. We know C, so now it's just a matter of just plugging stuff in, that lambda equals C, which is 3.00 times 10 to the 8th meters per second divided by the frequency, which is 3.74 times 10 to the 14th hertz, which is 1 over seconds. So when I do the math, the seconds are going to cancel out, and so I can get the wavelength. And the wavelength in this case, because of the speed of light is given in meters, is going to be in meters. So let's get out our calculators and let's do this. So that's going to be 3.00 times 10 to the 8th divided by 3.74 times 10 to the 14th. And so I get out of this particular equation, I get 8.02 times 10 to the minus 7th meters. So I don't ask for it in meters, I ask for it in nanometers. And so I know that in 1 meter there are 1 times 10 to the 9th nanometers. And so when I do that math, that should give me a wavelength of 802 nanometers when I do that math right there. So these are totally doable, my friends. It's just understanding what each of those Greek letters represent and then just doing the math. Now let's go on to number 2. How much energy is in each photon? Well, I have several ways of figuring that one out now. I'm going to use E equals H, which is Planck's constant, times the frequency. And so we can just plug and play right now. So Planck's constant is given. It is 6.626 times 10 to the minus 34th times the frequency, which I gave to you, which is in this case 3.74 3.4 times 10 to the 14th hertz. Okay, and so when I do that math, I'll just quickly put that in the calculator. 6.626 times 10 to the minus 34th times the hertz, which is 3.74 times 10 to the 14th. And so when I do that, I get 2.34 times 10 to the minus 19th, 19 joules, and that is joules for each photon. Those joules per photon. So here is my answer to number 2. That's my answer to number 1. And then the last one is, how much energy would 1.72 moles of photons contain? Well, I know that for each photon I have this many joules, and so now I can just do a quick conversion. I know that I start off with 1.72 moles of photons, and I know that in every mole of photons there is 6.022 times 10 to the 23rd photons, and I know that for every one photon there are, right here, 2.34 times 10 to the minus 19th joules. And so if we just do that math, 1.72 times 6.022 times 10 to the 23rd times 2.34 times 10 to the minus 19th. And so I get out of this, there are 2.42 times 10 to the times 10 to the 5th joules. So, assuming I did all my math right, these are the answers. Again, the tricks to this is just understanding that nu, the V-looking thing, is frequency, and that lambda is the wavelength. And just knowing these really basic equations. These are not hard problems to do. Sometimes I will give you something that will give you the wavelength instead of the frequency. Well, then you just manipulate this equation a bit differently. Always realize you know what C is, and if you have frequency, then you can always get the wavelength. When you have wavelength, you can always get the frequency. And then you can use this equation, E equals h nu, if you have the frequency. If you don't have the frequency but you have the wavelength, then you can use its companion, that is E equals Planck's constant times C divided by lambda, and you'll be given this equation. You'll be given these equations on the test. So be ready for a problem like this and know how to do it, and I think they're actually not too bad. You should be able to do it pretty easily.